Can we do 4.57?
I have to give you the specifics. Remind me to throw these out.
Find the mutual inductance between an infinitely long wire and a rectangular wire with dimensions shown in 4.58, which is
All right. The dimensions.
it's on the it's on the x and y axis.
And this says, give me the width of the thing.
It's width A and
Height.
height B, and it's P naught away from the y axis, sitting on the x axis.
Rho not away.
Yes.
Okay. This is classic. I think I did this actually. Does anybody remember me doing it at all? No. We're gonna get the mutual inductance now. So what we have to do first is get the magnetic flux here. So we're going to assume a current I up here, and that would cause a magnetic flux here, a value of B, to be equal to mu H, which is going to be equal to mu 0 right here times I over 2 pi rho in the A phi direction. If you want, you could do it this way. You could call this the actual x direction right here, or better yet, the y direction. And you could say that the actual, since that's y, this would be x coming out of the board, and therefore the H field, instead of putting A phi, you could put, if you want, you could put minus AX, but that's irrelevant. The mutual inductance will always be positive. Do you all follow me on this, class? Just like capacitance is always positive for any kind of a standard material. So, if we have that as the B field, and rho is measured from the radial axis, does everybody follow the logistics of this? Any question at all of why I'm doing what I'm doing right now? You have a simple square loop, it's assumed it's got a conductor on it, it's a single turn, you got an infinite wire, so we're going to find first the B field there, then we have to find the magnetic flux that penetrates that loop. You all with me? Everyone? And the flux is straight, so this is the symbol for magnetic flux. And that will be simply the integral of B dot ds. That's all it is over the surface. So the magnetic flux will be equal to, it'll be a double integral. Here's our B field, mu 0 I over 2 pi rho. You can put it in the A phi direction or minus AX, doesn't matter. It has to be dotted into ds. Does everybody follow me on this? That's the differential surface would have dimension d rho dz, correct? And it's going to be in the A phi direction. So it's going to be d rho dz in the A phi direction. Typically on a problem like this, I would actually make these either AX or AY, but it doesn't matter for this one because it is something that the flux is azimuthal, and the surface area will be perpendicular to the actual flux, the penetrating part. So A phi dot A phi is going to be 1. If you dot that out. Where does rho go from, class? Just take a look. Well, rho 0, right? That's this. It goes from rho 0 to rho 0 plus A. Y'all follow me? That would be the width integration. So rho goes from rho 0 to rho 0 plus the width. Where does Z go from? You can start anywhere, right? Start at 0, go to H, right? Because that's the height. Y'all follow me on this, class? You don't need to. You could put a point down here and call it A, and then end up at A plus that point, H, but it's really irrelevant. Make it 0. So you go from 0 to H. And what's that going to be? Well, I'm going to have mu 0 I over 2 pi, right? Now when we integrate dz, we get z evaluated from 0 to H is just H, right? And when we integrate 1 over rho d rho, what do we get, class?
Oh.
Natural log, right? Can everybody follow me on this? Y'all see what I'm doing, right? There's nothing tricky at all. So that's the natural log, and it's going to be of the upper, which is rho 0, plus W over the lower, which is rho 0. Now you can keep breaking this down. You can make it 1 plus W over rho naught. It doesn't matter, but that's essentially it for the flux. Follow me, everyone? Let me see this right. It's not hard. It's pretty apparent. So they get the magnetic, or the actual mutual inductance, M, or sometimes they call it LM, or L12. It doesn't matter from the first to the second system. Right here, that's just the actual flux divided by magnetic flux penetrating the region in 2 caused by the current in region 1 divided by the current. So that means that the mutual inductance is just going to be equal to mu 0 over 2 pi, right here, times h times the natural log of rho 0 plus W over rho 0, or just 1 plus W over rho 0. That's it in a nutshell. Now I have a couple comments about this. How many remember me doing this? Didn't I do this in your class?
You said you were going to do mutual inductance, but then we didn't get to it.
Didn't we get to the flux at least, going through that loop? I think we did that. That's mutual inductance. If you take the flux penetrating the second circuitry caused by the first current, the current in the first, that is the definition of mutual. Now something I'm going to mention about this that's really important. If you take a look at this, what happens is rho 0 goes to 0. In other words, what happens when this loop basically overlays there? Class, just look at the equation. Well, then I get W over 0, right, which is infinite. The log of infinity is still infinity, so it becomes infinite. Actually, it's undefined. And here's the reason I'm saying this. The wires, any physical wire has a radius. Y'all follow me? When you do mutual, you would go from the minimal possible distance away from that current source, which would be the radius of that current, the wire within the z-axis, all the way out to W. So just keep that in mind. Now another thing I talked about, this is for one single turn of wire. What's typically done is they're going to have something where they're going to have more than one turn like this. Y'all follow me in this class? They'll have, and you see this often in transformers and other things. You'll have wire that's either insulated with shellac, very thin, or they'll have some type of an insulator around it. They just wrap many, many turns on top of each other. So then what happens is, think about it, each one of those turns has that mutual inductance. So if you had n turns here on there, then the mutual inductance would need to be multiplied by n. You all follow me on that, class? And that's just, some of you had this in physics, I think. You probably had, who had power in here? Anybody? Do you remember this in power when Gross does this kind of stuff? He usually has he talks about mutual and self-inductance. No? Well, Gross does that typically, but anyway, so that's the mutual inductance. There's another part to this question?
That was it.
Again, I put it for any number of turns. That's how you do it. Another question?
So the only way this could get, the only way stuff, some like problem happens with this is if rho naught is 0.
Well, if rho naught's 0, then
So
it goes to infinity. It's a singularity. But here's another question for you. Now this loop is in the plane of the board, right? Just go with me on this, please. Assume that current still exists up and down here. Here's the original problem. This is the surface, right? What happens to the mutual if I do this? Anybody? Why? You're right. Why?
The angle between the two, isn't it? Just
The flux penetrating this is 0. Remember, the magnetic field's this way. The surface area is this way. I've made it so no flux penetrates. Y'all follow me? Now, what if I make it at a 45-degree angle? Now it's a reduced amount of flux from here, right? It'd actually be reduced by the cosine of an angle or sine of an angle, depending on which one. So if you take the cosine of the actual angle made, actually do the sine of the angle made between the normal component and the actual plane of this thing. So when it gets to here, I'm sorry, yeah, the cosine. When it gets to here, it would be the actual cosine of 90 degrees. If this is the plane, it goes to here, it would be a 90-degree angle, it would be 0. I'm just telling you this to be aware of these facts. I don't try to trick people about this, but you should be aware of how you have to get this as the amount of flux penetrating the loop normally. So if it's like this, it's how, you get the magnetic flux there and integrate over there. Now here, if you look at this, you can think of it as either a reduced surface area there, Or you can think about now it's not penetrating normally. The amount that penetrates normally is this, and then you would have to take a cosine of an angle to get the amount that's normal. Y'all with me on this, class? But it's always B dot ds, and the dot product takes care of all that stuff. All right, that's it. That is a classic problem. Another question, anybody? You got any other thing?
Yeah, can we do a 4.61?
Is this the toroid? Or did you, I mean, yeah. I think
Yeah, it's a magnetic circuit.
This is a great problem. The toroid, and the reason I'm saying that is, and some of these things I push, if I push homework up like this and I haven't covered all the material, it's made to cause you to question, have a natural question on an answer in class. All right, and that's the best way to learn, is have a question that you're really wondering about, and then have an answer. All right, this is 6-1, right?
Yes.
Go ahead.
A 2 centimeter diameter core of a toroid is characterized by the magnification curve of figure.
Oh, no, wait, I need to look at this.
Oh yeah,
Okay.
it's a lot.
Uh,
No, I'm
what's that?
I was reading the wrong one. Sorry.
All right, go ahead. I thought this was the toroid.
Yeah. With mu R1 equals 10,000.
Hold on, got it. Is this one you got a whole bunch of coils in?
Yeah.
All right, let me just, give me 1 second. I just want to get the idea. These coils go all the way around. With me, class? Now you're going to have some radius here. I think this is A. Then you're going to have a mean radius, I think, of B, and then an outer radius of C. Is this the same problem?
On the solutions, it's just a circle.
Well, I'm not worried about it. Is this problem? No.
4.61.
Problem 4.23. I got the wrong problem. You said 6-1?
Yes.
Okay. I'm sorry. This, I got you on this. This has got 2 different cores, right?
Mm-hmm.
Okay. Let me redo this one. This is a simple magnetic circuit that I'm going to talk. I might as well talk about it right now. So for this one, we have, and we have this as such, and you have so many turns here. I don't know how many turns, but I'll just call it N turns, right? And now they say the cross section of this actually looks like you have some inner material. Is it mu R1 on the inner?
Yes.
All right, so you have mu relative 1 here, and then mu relative 2 here, right? And what do they want?
The toroid has a 1 meter mean radius for 20 amps of current driven through 50 loops of wire. Find the
so
magnetic
B
field
is
intensity.
equal to what? What was that radius?
The mean radius is 1 meter.
All right. And go
And
ahead.
And there's 20 amps of current
Okay.
driven through 50 loops of wire.
All right, so
Find the
N equal
magnetic
50.
field
Go
intensity.
ahead.
Find the magnetic field intensity in each material of the toroid.
Okay. Now, for this one, I'm going to tell you something. I didn't cover magnetic circuits. How many have had magnetic equivalent circuits before? Anybody? I don't know if they do it in physics. I guess they don't. I don't remember if I had it in physics. I probably didn't. But here's what happens. We're going to build an equivalent magnetic circuit that parallels the electrical circuits that you're used to. Now, over here, you remember if you have an electrical circuit where you have just a voltage V, and you have something where you have resistance R, you will have a current that's called I. Everybody remembers that, right? That's very basic. And you know that V over I is given by R, or I is equal to, I'm sorry, let me do it this way. I is equal to V over R, and you can get R as considered the resistance in ohms, right? Now here is an equivalent magnetic circuit. Instead of a voltage, this is an equivalent magnetic circuit. You will have something called, something will have MMF, and that is magnetomotive force. So here, the MMF that is exactly like this is equal to N times I. think of it, N times I, as a voltage, a magnetic voltage, if you will, okay? Now, the next thing you have over here is something called reluctance, not resistance. The symbol in the book is this for reluctance. Now, if you remember resistance, I'm going to try to draw parallels, so hopefully this will help you see. Think about the electrical circuit. If we just have something with a constant cross-section, right here of A, and a given length L, and a given conductivity sigma, the resistance from there would be proportional to L, inversely proportional to A, and inversely proportional to sigma. Do you all remember that? How many do? All right, if you have, this is constant cross-section, given length of material, the resistance the material has along the long axis is going to be proportional to length, inversely proportional to cross-sectional area, and inversely proportional to sigma. You all follow me? How many remember that, please? Let me know. I hope you do. I mean, you guys remember this? This is just fundamental stuff. So over here, if you have a magnetic material with a given length L and a cross-sectional area A and a permeability mu, the reluctance of this between here and here, the reluctance is proportional to L, inversely proportional to A, and inversely proportional to mu. Now mu is mu relative, mu naught. But one thing I'm going to say about that magnetic reluctance you might think of as what opposes the actual magnetic field B. And this would be opposes the flux developed. Just go with me on this, you'll see how it works. So here I have reluctance. Now I complete the circuit. Then instead of having a current flow, you have a magnetic flux. And the magnetic flux is nothing more than MMF, or N times I, divided by the actual value of the reluctance. Now, magnetic flux is either in Webers or, I'll leave it in Webers. Are you with me on this, class? Now, if that's the magnetic flux, if you divided that, please, just listen. I've got the magnetic flux, right? How did we get the magnetic flux before? We integrated B dot ds. Do you all remember that? Right? So if you wanted the B field, once you had this, you can find the B field here to be equal to the magnetic flux divided by the cross-sectional area of the material. Now, in truth, the magnetic circuits really look like something like that, but I'm going to make it simple. Normally, they'll do it this way. You'll see a rectangular block like this, and it'll have a given cross-sectional area, so it'll look something like this. And without getting into all the details, you're going to have so many turns here, N turns. Each one of these turns has a current I. Well, this block has a total length around it. What they'll say is the reluctance of this, basically the reluctance of that, is going to be the total length. Then let's make it simple. Let's call this A and call the height A. So that it's really going to be the total length, which is 4A. And we can say that this thing has a cross-sectional area right here of A. So it's going to be divided by A and divided by mu. So mu. All right? Now that's the reluctance of the solid block. I'll spend a little more time on this, just trying to get you an idea of this. It's proportional to the length, inversely proportional to cross-sectional area, and inversely proportional to mu. And as mu goes to infinity, you can see the reluctance goes to 0. There's no such thing as going to infinity, but it gets very large. So back to this circuit, that's the B field. If you had the B field, how would you get the H field, class? Remember, you have mu. Yeah.
Multiply.
B is equal to mu H, right? So divide the B field by mu and you have H. All right? So if you take the B field and divide it by mu, you have H. Now, I think he has this in his book. I gotta check one thing. He shows you what I'm doing on page 272. But on the bottom of page 270, he actually shows you the equivalence of the parallels between electric and magnetic circuits. voltage he calls Vm, it's really N times I, and that's in the equation 4.106, right above it. This is on page 270 if you look. You want to look, you don't have to. But I'm trying to just point this out to you. The current is proportional to the magnetic flux. Now he uses phi for magnetic flux. I usually use psi, it's more common that way. And the resistance is the same, or it is directly analogous to reluctance. V equals IR, or Ni equals magnetic flux times reluctance, and mu is just like sigma. Can you all follow parallels? So now we'll do this problem based on that. By the way, with reluctances in parallel are just like resistances in parallel. Reluctances in series, just like resistances in series. Now we're going to come back to this. If you want to stay on that page, and you'll see how this works, because it's not very hard to understand what goes on. All right. Now we come over here in this cross section that I erased. It looks something like this. We have mu relative 1 here and mu relative 2 here. And I forgot the proportional distance. I mean, what's either the area or the radius or diameter of these?
The mean radius is 1 meter.
Well, that's this, right?
Yeah.
But for the cross section,
2 centimeter diameter core with a 1 centimeter thick layer of material on top of it.
okay, so let me erase that for a second. So he says he has something with a 2 centimeter diameter, right?
Mm.
And then there's a 1 centimeter
Wrapped around it, yeah.
thick, right?
Mm.
All right, that means this is 1 centimeter and this is 1 centimeter. Right? You all follow me? In is mu relative 1, the inner one,
Yes.
and mu relative 2 is the outer one. Okay. Now that, if you think about it, what we really have is 2 magnetic reluctances in parallel. You'll just look at that for a second. You all see this? If the magnetic flux is going to be flowing around here, that value, first we'll start with the equivalent magnetic voltage. Think of it as V, magnetic. That's equal to N times I. And I'll just put it here. It's equal to this. Whatever N is, whatever I is, we just put that there. The next thing we need is the reluctances. Well, this here looks like 2 reluctances in parallel. If you look at this thing, just think of it as a long pipe, right? If we didn't have this outer one, we just had the inner one, we would figure out the reluctance. Do you all follow me on that, class? And the reluctance of the outer one, without the inner one, is basically a hollow pipe, but they're in parallel. Can you all follow me on that? So what I'm going to do is get the reluctance first of the inner one. So I'll call it R1, and that's going to be proportional to the length. Can you all see the length as the total circumference? If you just cut this thing and straighten it out, it's the same thing. You all follow me? So that's going to be equal to 2 pi times the actual value of B. I'm going to leave it as B. Now I have to divide that by the cross-sectional area. I'm going to talk about the reluctance 1 being associated with this inner material that has mu relative 1, right? So that area, if that has a diameter of 2 centimeters, it has a radius of 1 centimeter. And the area would be what? Pi times, really, 10 to the minus 2 squared. You all with me on that? Everybody? Now B happens to be 1, so it's irrelevant. So when I look at the reluctance here, 1, the pi's cancel, I have 2b, b is 1, right? Over 10 to the minus 2 squared, or 10 to the minus 4. So it's really 2 times 10 to the 4th, and I forgot to divide by mu, and it's divided by mu, which is mu 0, and then it's times mu relative 1. Can everybody follow me on that? Don't worry about mu relative 1 yet. Just follow me as far as the method, right? I'm getting the reluctance of the inner one. Now, what's the reluctance of this part going to be? Well, it's proportional length, right? All the way around. 2 pi times b. Does everybody follow me on that? It's the total length around it, correct? Now I have to divide this by the area. What's the area here in the outer part?
Higher squared.
Well, if it was all made of that material, it would be pi times that radius squared, right? That radius would be 2 centimeters squared, right, from here to here. But we have to subtract the inner radius, right? Or the area and inside. So we end up with, we're going to need pi times, and this is going to be 2 times 10 to the minus 4th squared. That's the outer radius, minus the area associated with the inner radius, which would be pi times just 10 to the minus 2 squared. And then we have to divide it by mu, which is going to be mu relative 2, mu relative 1. So after all is said and done, the pi's will cancel, right? And then I have 2 over, and this is going to be 4 minus 1 or 3. That's going to be times 10 to the minus 4th. And that's going to be mu relative 2 times mu naught. And that would be the reluctance 2. They're in parallel, aren't they? You agree, class? So the circuit would now look like this, where I have the first reluctance here, and it's in parallel with the second reluctance. And they want the does he want the magnetic flux flowing through there first, or what does he want?
He wants the magnetic field intensity in each material of the toroid.
All right, we're going to first calculate the total magnetic flux. You all follow me? The reason behind it. Then we'll go from there. So when you take a look at that, and I'm going to try to do this sequential. The total magnetic flux, now he uses this symbol. Either symbol is fine. Magnetic flux would be Ni, right? And it's divided by the parallel values of those two. Well, if we have reluctances in parallel, the actual equivalent value is going to be 1 over reluctance 1 plus 1 over reluctance 2, just like parallel resistors. Does everybody follow me on that? Class? All right. So come over here, then we'll get the equivalent reluctance of these two. So that's going to be 1 over the first reluctance, so it's going to be mu 0 times mu relative 1 over 2 times 10 to the 4th plus mu 0 times mu relative 2 over 3 times, wait a second. Yeah, over, and that's going to be, oh, let me do this thing, understand? I'm going to take, that's the reluctance, so if I take 1 over this, I get mu 0, mu relative 1, over that is 2 times 10 to the 4th, plus, and this I can take the 10 to the 4th upstairs to be a little more understandable. When I take 1 over that, I get 3 mu relative 2, mu 0, over 2 times 10 to the 4th. So that means once I do this and go ahead and multiply top and bottom by 2 times 10 to the 4th. And then I can take out the mu 0. And I'm going to have mu relative 1 plus 3 mu relative 2. And that's going to be the reluctance. Everybody follow me on that? Now, he gives you values from mu relative 1 and mu relative 2, right? But does everybody follow me what I'm doing and what I'm doing? So this would be the total flux. I'm going to do something that's not asked for in this problem, but you're going to see what I'm doing. Now, how much flux is that, by the way? I mean, sorry, this is a reluctance. Can you tell me what this is? So this is 2 times 10 to the 4th here over This mu zero is 4 pi times 10 to the minus 7th. And well, what is mu relative 1? Can you just tell me?
1.768 times 10 to the 6.
0.768 times 10 to the 6.
That's R2, sorry.
Well, oh, sorry. What's mu relative 1?
Mu relative 1 is 1.592 times 10 to the 6.
Relative 1 is 10,000.
Yes, 10,000.
Which problem are you on?
We're on
Yours is
4.61, correct?
Is that right?
Oh, I thought you asked for reluctance.
It's 10,000.
Yes.
My brain ain't working.
What is this time? For mu relative 1?
Your
10,000.
relative 1 is 10,000.
10,000?
You're
10 to the
really
4?
answering.
I
Okay.
was reading the reluctance.
And what's
yeah.
mu relative 2?
Goodness gracious.
3,000.
Yeah,
3 times 3.
I was a little off there.
3,000,
Just my
okay.
brain numbers.
Yeah.
So, if you, can anybody just give me that value here? It's the parallel combination of the two. Tell you what, why don't we just do this one at a time? What's the reluctance here first? mu relative 1 is 10,000, right? 10 to the 4th, and mu relative 2 is 3,000, correct? So if you do that, what does this come out to be? Let's see. That's 4 pi,
little
that's
early.
10 to the minus 7 times 10 to the 4, that's still 10 to the minus, I can't do that.
1.592 times 10 to the 6.
Times 10 to the 6, is that right?
Flip it, yeah.
Okay, and what is this, R2?
1.768 times
Oh.
10 to the 6.
They were doing it in centimeters.
Is that right, class?
Oh,
No, they changed it. They
You're doing it in
changed it.
centimeters?
Yeah, they changed it.
Okay. Never mind.
Well, they're doing that. Look, we can get these values for sure. You can get the parallel equivalent of the two. I don't know what it is, but if those values are correct and they're in parallel, you can just take the first times the second over the first plus the second, or you can take 1 over the first plus 1 over the second. But what do you get for this, the parallel combination? Somewhere about 0.8 times 10 to the 6, something like that. Is that right?
Might be doing it. Yeah, I got like 8.37 or something.
Times 10 to the 5th for 6.
Close to
That's it? Well, look, when you use zeros,
Yeah, 8.38, 10 to the 5th.
8.3, that sounds better. 8.38 times 10 to the 5th. Is that right?
Yes, sir. Yeah.
Okay.
I think.
If we have that, now here's the reason I'm doing it. Next, I'm going to get the total flux here. So I'll take Ni. I'm going to put the values down. This is going to be Ni, right? Right here, divided by the reluctance total, equivalent. So N is 50, I is 20. So I have 50 times 20 over the total reluctance over 8.38 times 10 to the 5th. Now, what is that value of magnetic flux? I'll tell you what I'm doing. I'm going to show you something here. You can get the inductance for this in a direct way. This is important to see.
1.19, 10 to the negative 3.
1.19
Yes, sir.
times 10 to the minus 3, and that would be in Webers. All right? Now, over here, come back over here. We're going to get everything about this, the whole 9 yards. So the next thing I'm going to do is get the inductance. This is going to be the self-inductance. Now, inductance is always the total flux, which is really going to be, the symbol they use in the book is this, divided by the current causing it. Well, that symbol right there is called flux linkage, I think, in power and stuff like this. It's just the number of turns times the flux per turn over the current causing it. Well, the number of turns is 20, or I'm sorry, 50. 50 divided by the current causing that is 20. And the flux we just calculated right there, 8.38 times 10 to the fifth. Go with me on this? Right? Flux divided by current causing it is inductance. The flux is going through each one of those turns. So it's n times the flux through one turn. And you have to divide by the current causing it. What is this value? I don't think he gives it, but how many would you give for this?
Isn't 8.38 the reluctance?
I'm sorry. What's the flux? My bad. Oh, my bad. Yeah, you're right. It's 1.19 times 10 minus third. Sorry about that. So what is this going to be? You're absolutely right. So it's 5 halves times 1.19. 5, so it's about what, 3? Close to?
3 times 10 to the negative 3.
What's that?
3 times 10 to the negative 3.
Yeah, that's about right. About 3 times 10 to the minus 3 henries. That would be the inductance. Now, 3 millihenries is not really a big inductance by our standards. Y'all follow me? Now, they wanted what else did they want?
They wanted the magnetic field intensity of each material in the
Okay.
toroid.
So next, let me erase this part right here in the middle. Okay. There's a couple ways to do this. Now, always think of the parallels to electric fields, right? If they just want the magnetic flux, right, intensity, it's in Webers per meter squared. Just listen. This is like a voltage, right? If we wanted the magnetic flux flowing here, just down here, we would take the voltage divided by the resistance if it was an electric circuits problem, right? Here, you just take the magnetic voltage, or I'm just going to put it this way. Magnetic flux in 1 is simply going to be Ni divided by the reluctance 1. That would be in Webers. Then we divide it by the cross-sectional area to get the value of the B field. Remember, this is in Webers, B field is in Webers per meter squared. So just bear with me here. So first, this has to do with material 1, or mu relative 1. What is the B field? So first we find the magnetic flux flowing in 1, and that's going to be Ni divided by the reluctance in 1, which is 1.592 times 10 to the 6th. That's the magnetic flux flowing in the first one. You all follow me on that, class? Then I divide by the cross-sectional area of the first one. So then I have to divide this by the cross-sectional area to get the B field 1. So the cross-sectional area in 1 is, what? Pi times 10 to the minus 2 squared, or really it's pi times 10 to the minus 4th, right here. And that would be the B field in 1. So that's 20 times 50 over this. Can somebody give that to me?
It equals 2.
What?
2.
I mean, did you calculate or just read?
I just read.
Can somebody just calculate to make sure? I mean, I like Wentworth, and his books generally are right up on solutions, but some of this, there's enough places to make mistakes. I want a calculation from somebody. It's going to be close to 2, I think. But I can't just look at that. I got Ni, so that's 20 times 50.
I got
What is this? What do you get?
1.999.
Okay. So the B field in region 1 is 2. Now, what's the B field in region 2? You do it. Think about it. Well, what's the flux flowing here? Class? Can y'all follow me on this one? Everybody's quiet. Is it church house? Anybody? What's the flux? Well, if I take what? Ni, right? Then I have to divide by the reluctance 2, this. Do you all agree with this? Right, that's the reluctance 2. 1.768 times 10 to the 6th, right? Now, that would be the flux, right? What do I have to do next?
Divided by the area.
Divide by the area, because flux is in Webers, B field is Webers per meter squared. What's the area in region 2?
10.
I erased it, but it's the outer part, right? It would be pi
Times
b
2
squared, which is
minus
pi times 2 times 10 minus 2 squared,
minus
minus pi a squared, and really it's going to be what? That's going to be pi times 10, or it's really going to be 3 pi, right, times 10 to the minus 4. Do you all agree with that, class? That's just the area of the outer part. So what is that? That mean? Calculate it. Don't. I know you can look it up. It's the B field in region 2. I got
0.6.
Anybody confirm 0.6? Is that right?
Yeah, I got that. That's correct.
All right. 0.6 Webers per meter squared. This is 2 Webers per meter squared for the first part. All right, so we got the B field. Now, question. This is like a question I would ask on a quiz. Hint, this is a question I would ask on a quiz. How do you get the H field in 2 regions? If I wanted, I'm going to erase this right here. We know what it looks like. So, how do I get the H field in region 1? Well, what is B equal to mu H, correct? We've got B, we've got mu. We take B over mu to get H. Do y'all follow? I'm going to show you something here that's very interesting, then I can draw parallels. So what's the H field in region 1? I take the B field in region 1, which is 2 Webers per meter squared, right? And I divide it by mu in region 1, right? What's mu in region 1? Mu naught times 10,000, is that right? Correct? What do you get for that? Give me a value. You may not have that. Remember, mu 0 is 4 pi times 10 to the minus 7. It's Henry's period. Anybody? Go ahead. You got a calculator. Do this with me to help you.
159.2.
159.2. All right. Now that would be what? That's amps per meter of the units, whether you know or not. It takes a while to get familiar with the units. Now what's the H field in region 2, people? That's the B field in region 2, right? So it's going to be what? 0.6 divided by what? Mu 0 times, and what is it 3,000?
3,000.
Divided by 3,000. What do you get over here? I'm not trying to bore you. I'm trying to make sure you understand the steps that are necessary to take to get this. Anybody?
159.2.
Same thing.
Identical. All right. My point is this. Just think about it, right? Here, these are in parallel, right? Now, the H field is like the E field. Think of it that way. H is parallels the E field. One thing you know about E field is E tan 1 is E tan 2. The tangent E field is the same, right? Across a boundary. Here I erased it, but you have a boundary where the actual magnetic flux, where the B field is circular, and so is the H field. It's like the E field. Think of it that way. So the H field in one region has to be the H field on the other region. It has to be. Something else, just think to yourself. You know how E dot dl is the voltage? Remember that. The integral of E dot dl is the voltage. If you just take E times L, if E field doesn't change and it's in the direction of L, E times L would be the electrical voltage, right? Now, the magnetic voltage is like N times I. Didn't I just say that? So, if you actually take the length around, I'm going to do it right here. If you take the total length you go around, which is 2 pi times the mean radius, and I'll do it right here, times the H field, you'll get Ni. think about this for a second, I have Ni is like the magnetic voltage, if you will, and that's 20 times, I guess, 50, or 50 times 20, and that is equal to the H field. We have an H field of
159.2.
yeah, sorry, 159.2. Now, think about this. Well, let me just do this down here. Now I'm going to take the integral of H dot dl, which will be equal to the H field of 159.2 times the length, which is 2 pi, right? And the mean radius is 1, correct, class? So what's this value? Just tell me what this value is. I can't do that. 160, 320 pi, oh,
1,000.28.
what is it?
1,000.28.
What's this?
1,000.
Second. Y'all follow me? This is how all this stuff works, the magnetic stuff. A lot of this stuff, I didn't give you many problems. I gave you enough to make you think about it. But if you have any kind of a structure like a toroid or anything like that, and all the magnetic field you can assume is confined to that system, you can get the actual inductance, you can get the magnetic field, the H field, magnetic field intensity, and you can get the H field in amps per meter. You can also get the magnetic energy. Now, hear me on this. And I'm going to show this here. This is actually a pretty interesting problem. A lot of this stuff you're going to get in power. I think you've had power already, or you take
it right now.
All right, in power, Dr. Gross, whoever gets to teach, he'll go through a lot more depth of this, and actually its applications to transformers and things like that. But you can almost see that this problem has the makings of either an inductor, if I put a second coil, or transformer. You all follow me on that, class? So now, one thing to think about, if you just have your basic inductor, that's what our circuit would be equivalent to in terms of a lumped element that we just did. That's all it is. Well, if you have an inductor with a current I, what is the total energy? What is the magnetic energy in there? Total energy. How many remember? We could do 1/2 the integral of mu magnitude of H squared over the volume. We could do that. You all follow me? That would be the magnetic energy density integrated over the volume. But remember, when you have an inductor, the magnetic energy is what? 1/2 Li squared. How many remember that? Okay, you should. By the way, with an inductor, you also have a voltage that you develop across an inductor. And that voltage is L times di dt, right? No change in voltage. I mean, no change in current, no change in voltage. It's constant, 0, right? All right, now, I'm really trying to link this to things you know and need to know. Now, did we calculate the inductance? We did, right? Can we get the magnetic energy? Sure, right? You give me a current, I think it was 20, right? We have the inductance. What was the inductance again? Do I have it up there or not? I guess not. We had the inductance, right?
One, oh, no, I don't know.
Pardon me?
3 times 10 negative 3 henries.
Say it again.
3 times 10 to the negative 3 henries.
All right, you can get the magnetic energy stored in there. For any, I mean, if it was 20, we would take 20 and square it, right? And that would be 400. 400 times that would be the energy in joules, right? Some of this stuff it becomes real important when you're doing things where you've got energy stored and you've got to extract it through a system. And this is a little later on, but you all found an appreciation for how to do this? Let me ask you this. Well, go ahead. Do you have another question? Oh, I'm over. Can't believe I'm.
Is the quiz Friday going to be on magnetic circuits?
It is now. It wasn't going to be it, but after the amount of time, I'll give you some more homework on this. I didn't realize I ran out of time. I thought I had at least 20. All right, it will be. And what I'm going to do too, I'm going to give you some more homework. Now, I want to kind of go through this. I'm going to go through magnetic forces on Friday, which are real important. And I'm going to go through a couple other things that have to do with magnetism, but primarily, I'll do the full transformer bit on Friday if I have time. And we'll talk about the magnetic lifting capability of magnets. You all know that basically that they use a magnet, an electromagnetic, like lift cars and stuff like this and track. And so we're going to go through how you actually calculate the magnetic force for electromagnetic stuff like that. But I'm going to go through all this. And if I have time, and I'm thinking, well, Friday, but at some point I'm going to take you through railgun, and that's something that we actually built long ago. And we had all of it. Well, the students loved it. They were maniac guys, and we were shooting over a mile a second. Right, that's 5,280 feet per second and faster. Mod 6, 30.6 goes about 3,000 feet per second. So when these guys saw this, they just, now they saw what they needed to kill that deer. Anyway, we had a blast with that thing. Those guys, they had more fun with that than I think any other senior design I've ever seen.